Hello, and a very warm welcome to the Snoozy Scientist. I'm truly so glad you found your way here, to this quiet corner of curiosity, whether you're nestled in your bed with the lights turned low, resting peacefully on a comfortable sofa, or perhaps just letting your thoughts soften after a long day. This space is crafted just for you. Please, make yourself as comfortable as you possibly can. Tonight, we're going to take a quiet journey together. We'll be drifting far from our small familiar world out into the deep and silent expanse of the cosmos. Our destination is a place of profound transformation, where we'll witness one of nature's most spectacular and fundamental events, the quiet cosmic goodbye of a star. We will gently explore what happens when these celestial giants reach the end of their long lives, and how their passing gives rise to some of the universe's most mysterious wonders, the brilliant flare of a supernova and the silent deep gravity of a black hole. Now, I feel I should offer a small, gentle note of caution. I've done my very best to make this journey a deeply peaceful one, but the universe is a rather fascinating place. There is a small chance that our exploration might become a little too captivating. If it happens to keep your mind gently engaged rather than drifting off to sleep, well, I hope you'll forgive me. At least you'll drift off eventually, perhaps a little wiser about the stardust that makes up our world. If you're already feeling a sense of calm settling over you, I would be ever so grateful if you considered giving this audio a gentle like, and maybe even subscribing for more moments of cozy discovery like this. It truly helps more sleepy minds find their way to our shared space. And if you feel so inclined, I always love to see where in the world you're listening from, so perhaps leave a little note in the comments. It's a joy to watch our map of peaceful listeners slowly light up across the globe. Finally, as always, this audio is created purely for relaxation and educational enjoyment. It is not, nor is it intended to be, medical advice, so let's begin. Let's take a slow, deep breath together, breathing in and gently out, and let your mind's eye drift upwards, past the ceiling, past the atmosphere, into the velvety, star-dusted dark. Before we can speak of endings, it feels only right to first understand the beginning. Before a star can die, it must, of course, live. But what is a star, really? We see them as tiny, twinkling points of light, distant and serene. But up close, they are vast, powerful engines of creation, and their lives are a story of a perfect, delicate balance. The story of every star begins in a place that sounds as gentle as it looks, a stellar nursery. Imagine vast, cool gossamer clouds floating in the blackness of space. These are called nebulae. They aren't empty voids, they are unimaginably immense clouds of simple gas, mostly hydrogen, and tiny specks of cosmic dust. The leftover ashes from a previous generation of stars. These nurseries are some of nature's quietest, grandest cradles, stretching for light years across. For millions of years they just drift, seemingly unchanged, but nothing in the universe is ever truly still. Deep within these clouds, a tiny, almost imperceptible whisper of gravity begins its work. Perhaps a passing star sends a gentle ripple through the gas, or the shockwave from a distant cosmic event gives it a nudge. In a region of the cloud that is just a little bit denser than the space around it, gravity starts to pull the gas and dust particles closer together. Very slowly, over an immense stretch of time, this gentle gathering forms a clump. It's a bit like a single snowflake forming around a microscopic speck of dust, but on a cosmic scale. This dense, warming clump of gas is not yet a star. It's a stellar embryo, known as a protostar. As more and more material falls inward, the pressure and temperature at the core of the protostar begin to climb. It starts to glow, not with the brilliant light of a true star, but with a dull, warm, infrared light. the heat of its own compression. For tens of thousands of years, it continues to gather mass from its parent nebula, growing ever denser, ever hotter. And then, a moment of magic happens, a threshold is crossed. When the temperature at the very centre of the protostar reaches about 10 million degrees Celsius, something incredible ignites. The heart of the protostar awakens. This is the beginning of nuclear fusion. The immense pressure fuses the simplest atoms, hydrogen, A, into the next simplest, helium, She. This isn't an explosion in the way we might think of one. It is a constant, steady, controlled reaction that begins to radiate an enormous amount of energy outward from the core. This is the star's first breath. It is the moment it is truly born. This new outward-pushing energy from fusion creates a perfect counterforce to the relentless inward pull of gravity. And this is the secret to a star's long and stable life. A state of perfect harmony called hydrostatic equilibrium. Imagine holding a balloon. The rubber of the balloon is constantly trying to collapse inward, but the air you've blown inside is pushing outward, keeping it perfectly inflated and round. A star is much the same. Gravity is the hand trying to crush it, and the energy from nuclear fusion is the breath pushing back. For as long as these two forces remain in balance, the star will remain stable. This long, stable adult phase of a star's life is called the main sequence. Our very own Sun is in this phase right now, a calm middle-aged star in the prime of its life, steadily turning hydrogen into helium in its core. For a star the size of our Sun, this tranquil period lasts for about 10 billion years. 10 billion years of that gentle, constant hum of fusion, providing light and warmth in a perfect, reliable balance. It's a life of profound stability, a slow and steady burn that makes life as we know it possible on the planets that are lucky enough to orbit it. So this long, stable life, this main sequence, is where a star spends the vast majority of its existence. Billions of years of quiet, dependable light. But no fuel source, not even one as immense as a star's, can last forever. Like a bank account that is only ever withdrawn from, the hydrogen in the star's core eventually begins to run low. And this is where the star's story takes a turn, beginning its slow and graceful journey towards its end. This is the star's celestial autumn. The core, which was once a bustling factory turning hydrogen into helium, becomes slowly filled with the inert ash of that fusion, a dense, hot ball of helium. With the primary fuel in the core exhausted, the fusion process there sputters and stops. The delicate dance of hydrostatic equilibrium is broken. Without the outward push of fusion from the core, gravity begins to win. The helium core starts to compress under its own immense weight, and as it compresses, it grows even hotter. This intense heat from the contracting core radiates outwards and ignites the layer of hydrogen that still surrounds it, like lighting the kindling around a hot coal. Fusion begins anew, but not in the core anymore. It now happens in a shell around the core. This shell fusion is actually far more intense and furious than the core fusion ever was. This new, powerful outward pressure dramatically overwhelms gravity's pull. The result is that the star's outer layers begin to expand and expand and expand. The star begins to swell to an enormous size, growing hundreds of times larger than it was during its main sequence life. It becomes what we call a red giant. If our own Sun were to become a red giant, its outer atmosphere would swell to engulf the orbits of Mercury, Venus, and perhaps even our own Earth. It is a silent, slow-motion swallowing, a final warm embrace of its closest children, but thankfully it's an event that is still billions of years in our future. You might wonder why it's a red giant. As the star's surface expands so vastly, its energy is spread out over a much larger area. This means the surface temperature actually drops, causing it to glow with a cooler, redder light. So while the star is vastly more luminous overall, its colour shifts from a brilliant yellow-white to a deep dusky orange or red. We can see examples of this in our own night sky. The star Betelgeuse, in the shoulder of the constellation Orion, is a famous red supergiant, a star nearing the end of its life, swollen and glowing a beautiful fiery red. But the story isn't over yet. For a star like our Sun, there is another chapter to its life. As the star exists in its red giant phase, the helium core at its centre continues to contract and heat up. Eventually, the temperature in the core reaches a new magic number, about 100 million degrees Celsius. At this incredible temperature, a new kind of fusion can ignite. The helium atoms themselves begin to fuse together, creating heavier elements like carbon, C, and oxygen, O. In a star of our Sun's mass, this ignition of helium happens in a sudden runaway event called the helium flash. It's an incredibly powerful event, but it happens deep within the dense core, and its energy is absorbed by the star's outer layers, so it's not something we would see from the outside. It's like a deep internal sigh of relief. The flash brings the core back into balance, and the star actually shrinks a little, becoming smaller, hotter, and more yellow again. It finds a new, though much shorter period of stability, now with two sources of energy, a helium-fusing core and a hydrogen-fusing shell around it. The star has been given a second wind. This second life, however, is brief. Helium fusion is far less efficient than hydrogen fusion, and this new fuel source is exhausted in a mere few million years. A blink of an eye in cosmic terms. The core, now made of carbon and oxygen, becomes inert once more, and the process repeats itself. Gravity again takes over, the core contracts, and the shell fusion flares up with even greater intensity. The star swells up for a second time, becoming even larger and more luminous than it was during its first red giant phase. This is the stage known as the asymptotic giant branch, AGB. An AGB star is a truly magnificent and unstable object. With its core of carbon and oxygen, a shell of helium fusing into carbon around that, and another shell of hydrogen fusing into helium around that, its internal structure is like a delicate cosmic onion. In this final majestic phase of its life as a giant, the star becomes very unstable. Its gravity at its vast bloated surface is now very weak, and it begins to shed its outer layers into space. A powerful stream of gas and dust, called a stellar wind, flows away from the star like a final grand exhalation. It is slowly returning its substance to the cosmos from which it came. This process of mass loss is gentle but persistent, and it's the key to what happens next, creating one of the most beautiful sights in the universe. This process of a star shedding its outer layers, this final grand exhalation, is not a violent explosion. It is a slow, pulsing release that continues for thousands of years, sending the star's atmosphere drifting out into the void. This expanding cloud of gas, illuminated by the star's now exposed core, creates one of the most sublime and breathtaking objects in the entire cosmos, a planetary nebula. Now, the name is a little misleading, a charming mistake from a time of simpler telescopes. When early astronomers like William Herschel first spotted these objects in the 18th century, they saw faint, round, ghostly discs of light that looked, to them, like the newly discovered gas planets, Uranus and Neptune. They called them planetary nebulae, and the beautiful poetic name has stuck. Even though we now know they have nothing at all to do with planets, they are in fact the swan song of a dying star. As the star's outer layers drift away, they unveil what's left at the centre, the star's heart, a tiny, intensely hot, and incredibly dense core of carbon and oxygen. This stellar remnant is called a white dwarf. This newborn white dwarf is blisteringly hot, with a surface temperature that can exceed 100,000 degrees Celsius, far hotter than the star was during its life. It shines with a brilliant white-hot light, flooding the surrounding space with intense ultraviolet radiation. This is where the magic happens. This ultraviolet light streams out from the central white dwarf and crashes into the expanding gas cloud that it just shed. The energy from the light excites the atoms in the gas, causing them to ionize and glow with spectacular colours, like a vast cosmic neon sign. The specific colours we see are the fingerprints of the elements the star created during its lifetime. Hydrogen gas glows a soft, rosy red. Oxygen glows a beautiful ethereal shade of teal or green. Nitrogen adds another shade of deep red. The result is a celestial masterpiece, a glowing ghost of a star, painted across the darkness in breathtaking hues, and their shapes are just as varied and beautiful as their colours. While some are simple, serene rings of light, like the famous Ring Nebula, others are sculpted into far more complex forms. We see nebulae shaped like delicate butterflies, with vast wings of gas stretching for light years. Others look like celestial hourglasses or intricate swirling patterns that hint at a complex and dynamic history. These beautiful shapes are likely sculpted by the star's rotation, its magnetic fields, or perhaps the gravitational influence of a hidden companion star, all working together to shape the outflowing gas into a unique work of cosmic art. But let us turn our attention back to the heart of the nebula, to the white dwarf itself. This object is one of the most extreme forms of matter in the universe. It is the collapsed core of a once mighty star, now shrunk down to roughly the size of the Earth. Yet, it still contains about half the mass of our entire Sun packed into that tiny volume. The density is almost beyond comprehension. A single teaspoon of white dwarf material would weigh several tons on Earth. It is a stellar ember, a cosmic diamond. You might wonder, with all that mass and all that gravity, why doesn't it collapse further? It is held up by a remarkable quantum mechanical principle called electron degeneracy pressure. You can think of it like this. Matter is mostly empty space, with tiny electrons orbiting the nucleus of an atom. Gravity wants to crush all that empty space away, but electrons are stubborn particles. They fundamentally resist being squeezed into the same space with the same energy state. In a white dwarf, the matter is crushed so densely that the electrons are pushed as close together as quantum mechanics will allow. They create a powerful counterpressure, an unyielding wall that says to gravity, this far and no further. The star is now supported not by the heat of fusion, but by this strange and powerful quantum rule. A white dwarf no longer generates any new heat. It is a dying ember, and its only remaining story is to slowly, incredibly slowly, cool down. It will radiate its leftover heat into space over an immense timescale, gradually fading from brilliant white to yellow to orange to red. Finally, after trillions of years, a timescale far, far longer than the current age of the universe, it will cool completely, becoming a cold, dark, invisible object known as a black dwarf. Since the universe is only about 13.8 billion years old, no black dwarfs are thought to exist yet. They're a vision of the universe's far, far future. And what of the beautiful planetary nebula? Over tens of thousands of years, it will continue to expand and disperse, its beautiful colours fading as it drifts further from its central star. The elements it contains, the carbon and oxygen forged in the heart of its parent star, will mix back into the interstellar medium. This enriched gas will one day become part of a new nebula, a new stellar nursery, providing the raw material for the next generation of stars and perhaps the next generation of planets and life. The gentle death of a small star is not an end. It is a quiet, beautiful, and vital act of cosmic recycling. This quiet fading, this slow transformation into a glowing ember and a ghostly nebula, is the destiny for the vast majority of stars in the universe, including, one day, our own sun. It is a story of grace, beauty, and renewal. But it is not the only story. What about the giants, the celestial titans born with 8, 10, 20, or even 100 times the mass of our sun? Do they also end their lives with such a gentle sigh? Does their immense energy simply drift away like smoke? No, their story is different. A life lived with brilliant intensity must also have an ending of unimaginable power. For these massive stars, the final act is not a quiet fading, but a spectacular universe-altering event, a type supernova. To understand this incredible ending, we must first go back and understand their unique lives. A massive star is born from the same cosmic nurseries as its smaller siblings, but its great mass dictates a very different path. The immense gravitational force of a massive star creates truly colossal pressures and temperatures at its core. Think of the gentle furnace at the heart of our sun, and then imagine one that burns hundreds of times hotter and more ferociously. This intense internal environment means that a massive star burns through its hydrogen fuel at a truly prodigious rate. It is the cosmic equivalent of live fast, die young. While our sun will enjoy a stable life for 10 billion years, a massive star might exhaust its core hydrogen in a mere 10 million years. It shines with a brilliant blue-white light, thousands of times more luminous than our sun, but its life is but a fleeting moment on the cosmic clock. When such a star runs out of hydrogen in its core, it too begins to swell, but on a scale that dwarfs the red giants we spoke of earlier. It becomes a red supergiant, a behemoth so large that if one were placed at the centre of our solar system, its surface could extend out to the orbit of Jupiter or even Saturn. Stars like Betelgeuse and Antaeus are prime examples of these colossal ruddy titans. Here is the most crucial difference. After exhausting the hydrogen and then the helium in its core, the star does not stop. The gravity of a massive star is so powerful that as the carbon-oxygen core contracts, it can reach the staggering temperatures needed to ignite the fusion of carbon itself. And so begins a frantic, cascading series of reactions deep within the star's heart. The star develops a complex, layered structure, like a cosmic onion. As the core burns through one fuel, it creates a new, heavier element as ash. This ash then contracts until it becomes hot enough to become the next fuel source. Carbon fuses to create neon. Neon fuses to create oxygen. Oxygen fuses to create silicon. And each of these stages happens faster and faster. Hydrogen burning lasted millions of years. Helium burning hundreds of thousands. Carbon burning a few hundred years. Neon burning just 1 year. Oxygen burning might last for a few months, and the final stage, silicon burning, might last for only a single day. In the last day of its life, the star's core frantically converts silicon into a range of heavier elements, all centered around the most stable element of all, iron, Fe. The star's core is now a dense ball of iron, roughly the size of the Earth, surrounded by concentric fusing shells of silicon, oxygen, neon, carbon, helium and hydrogen. A beautifully complex structure, but one that is poised on the brink of catastrophe, because iron is the end of the road. It is the final ash of stellar nucleosynthesis. Every fusion reaction up to this point, from hydrogen to silicon, has released energy. It is this released energy that has held the star up against the crushing force of its own gravity for millions of years. But fusing iron is different. Fusing iron atoms together does not release energy, it consumes it. It takes more energy to make it happen than you get out of it. It's like trying to burn ash. And so for the first time in the star's life, its core is no longer an engine. It is an energy sink. The furnace at the heart of the star has gone out. The outward pressure that supported the star for its entire life vanishes in an instant. There is now nothing holding back the unimaginable weight of the star's outer layers. The iron core, the final product of a lifetime of fusion, has become the agent of its own demise. In the final moments of stillness, trillions upon trillions of tons of stellar material hang suspended above a core that can no longer push back. The stage is set for the most violent and powerful event in the known universe. What follows happens in less time than it takes for me to say this single word. It is a process of such speed and violence that our human senses of time and scale can barely comprehend it. But we can walk through it, moment by moment, in our minds. With the furnace of fusion extinguished, the force of gravity is now completely unopposed. The core collapse begins. The iron core, that dense ball the size of our Earth, begins to fall inward on itself. This isn't a fall like a stone dropping from a cliff. It is a synchronized, instantaneous implosion. The outer edge of the core and the center of the core arrive at the middle at almost the same time, rushing inward at speeds reaching up to 70,000 kilometers per second, nearly a quarter of the speed of light. In less than a second, the core shrinks from the size of a planet to the size of a city, a tiny hyperdense sphere just a few dozen kilometers across. The temperature and pressure skyrocket to levels that are truly astronomical, temperatures in the hundreds of billions of degrees and densities far beyond anything we've discussed so far. The conditions become so extreme that the star's own energy turns on itself, beginning to undo the work of a lifetime. The intense gamma radiation becomes so powerful that it starts to smash the iron nuclei apart. This process, called photodisintegration, is like a cosmic demolition crew, breaking the complex iron atoms back down into simpler helium nuclei, and then further still into their basic building blocks, protons and neutrons. This process is horrifically efficient at absorbing energy, stealing the heat from the core and robbing it of any remaining pressure. It's like pulling the last structural supports from a building that is already collapsing, causing the implosion to accelerate even faster. At the same time, the density becomes so great that it finally overwhelms the electron degeneracy pressure, that quantum rule that holds up a white dwarf. Gravity is so strong here that it physically forces the tiny electrons into the protons. They merge, cancelling out their opposing charges to form a neutron, and in the process, release a tiny ghostly particle, a neutrino. This process of neutronization sweeps through the collapsing core, turning the once familiar matter of protons and electrons into a strange new substance composed almost entirely of neutrons packed shoulder to shoulder. This conversion releases a staggering flood of neutrinos. In these few seconds, the dying star radiates more energy in the form of these tiny neutral particles than our Sun will in its entire 10 billion year lifetime. For a brief moment, the supernova shines brighter in neutrinos than all of the other stars in the entire observable universe combined. But neutrinos are famously elusive. They barely interact with other matter. Trillions of them are streaming through your body right now, having travelled from our own sun, and you don't feel a thing. This immense flood of neutrino energy streams out of the core almost instantly, carrying away the memory of the collapse, and leaving the core even colder and more compressed. But the collapse cannot go on forever. When the core has been crushed down to the density of an atomic nucleus itself, a new force finally says, stop. It is a force similar to the one that held up the white dwarf, but now it's between the neutrons. It's called neutron degeneracy pressure. The neutrons are packed so tightly that they refuse to be squeezed any further. The core in an instant becomes the hardest, most rigid substance in the universe. The inner part of the core stops collapsing, but the outer parts are still raining down at a quarter of the speed of light. This material smashes into the newly formed incompressible neutron core and rebounds. It is the most powerful bounce in history. Imagine throwing a rubber ball against a solid steel wall. Now imagine that ball weighs more than our sun and is moving at unimaginable speed. This rebound creates a colossal shockwave of pressure and energy, an invisible wall of force that begins to travel outwards, away from the core. This shockwave is the beginning of the explosion. It carries with it the power to tear the rest of the star to pieces. But as this shockwave begins its journey, it has to fight its way out of the star's incredibly dense heart. The very material that is still falling inwards onto the core pushes against the shockwave, trying to smother it before it can even get started. For a critical moment, deep in the heart of the dying star, the mighty shockwave stalls, its immense energy held in a delicate, temporary balance. The explosion has been lit, but the fuse is struggling to burn. It needs another push to finally succeed and announce the star's death to the universe. The shockwave is stalled, trapped by the immense pressure of the star's own infalling layers. It seems as though the explosion might fail, fizzling out into a black hole without a grand announcement. But there is a hero in this story, a tiny, ghost-like particle that we have already met, the neutrino. We said that most of the neutrinos from the core collapse stream away into space unimpeded, but most is not all. In the incredibly dense region just behind the stalled shockwave, a small fraction of them, perhaps only 1%, get momentarily stuck. They're absorbed by the superheated, compressed matter, and in doing so they deposit their tremendous energy into it. It's a gentle process, but the sheer number of neutrinos involved makes it unimaginably powerful. That 1% is enough. This injection of energy is the final push the shockwave needs. It's like a hand reigniting a sputtering fuse. The shockwave is reborn, re-energized, and now it has enough power to overcome the infalling matter and continue its journey outwards. The star's fate is sealed. With renewed and unstoppable force, the shockwave now tears its way through the outer layers of the star. It rips through the shell of silicon, the shell of oxygen, the shell of neon, and all the others that make up the star's cosmic onion structure. This process is not just destructive, it is profoundly creative. The passage of the shockwave creates a fleeting, intense flash of heat and pressure, far hotter and more energetic than anything the star experienced in its stable life. For a few brief seconds, this environment is a crucible for a new kind of alchemy, explosive nucleosynthesis. The intense energy allows for the rapid creation of elements far heavier than iron. It is in these fiery moments that the universe forges its most precious materials. The gold in a wedding ring, the silver in a coin, the platinum in a catalyst, the uranium that powers reactors. Nearly every atom of every element heavier than iron in the universe was born in the heart of a supernova explosion like this one. The star in its death throes is a cosmic forge, seeding the future with richness and complexity. It may take several hours for the shockwave, travelling at thousands of kilometres per second, to finally fight its way to the star's vast surface. For all this time, the cataclysmic events at the core have been hidden from the universe. And then it happens. The shockwave breaks through the surface of the star in a brilliant burst of energy known as the shock breakout. This is the first visible light of the supernova, an intense flash of high-energy X-rays and ultraviolet light that signals the beginning of the main event. The star begins to brighten at an incredible rate. The material of the star's outer layers, now known as the ejector, is blasted outwards into space, expanding in a fireball that can be trillions of kilometres across. For a period of a few weeks or months, this single dying star can become as bright as an entire galaxy containing hundreds of billions of stars. It is a beacon of light that can be seen across unimaginable cosmic distances. This incredible sustained brightness isn't just from the initial heat of the explosion. It's powered by a secondary internal engine, the radioactive decay of the new elements forged in the blast. Specifically, a large amount of an unstable isotope of nickel 56I is created. This nickel rapidly decays into an unstable isotope of cobalt 56Co, which in turn decays into stable iron 56Fe. Each of these decay steps releases energy in the form of gamma rays, which heat the expanding gas and cause it to glow brightly, like a celestial lantern powered by a radioactive core. This light is a message, travelling across space and time, telling the story of the star's demise. In 1987, astronomers witnessed a supernova in a nearby galaxy called the Large Magellanic Cloud. Crucially, they detected the burst of neutrinos just a few hours before they saw the first light, a perfect confirmation of our story of core collapse. And centuries ago, in the year 1054, Chinese and Arab astronomers recorded the appearance of a new guest star in the sky, one so bright it was visible during the daytime for weeks. Today, we can point our telescopes to that very spot and see the beautiful expanding cloud of the Crab Nebula, the glowing remnant of that same stellar explosion, its message still reaching us 1,000 years later. The brilliant light of the supernova eventually begins to fade. The radioactive glow dies down as the unstable elements decay into stability. But the story of the explosion is far from over. The physical material of the star, that vast cloud of ejecta carrying the newly forged elements, continues to expand outwards into space for thousands upon thousands of years. This ever-growing, glowing cloud of gas and dust is known as a supernova remnant. These remnants are among the most beautiful and complex structures in the galaxy. They are not uniform, expanding bubbles. They are intricate, tangled webs of filaments, sheets and knots of gas, glowing in soft hues of red, blue and green. The famous Crab Nebula is a young supernova remnant, still energetic and compact, powered by a secret at its heart that we will soon discuss. Older remnants, like the delicate and vast Veil Nebula, have expanded to stretch across huge swathes of the sky, looking like a celestial soap bubble caught in the light. As this shell of stellar debris travels outwards at incredible speeds, it acts like a cosmic snowplow. It slams into the thin, cold gas and dust that drifts between the stars, the interstellar medium. This collision creates another series of shockwaves which heat the gas to millions of degrees, causing it to glow brightly, primarily in X-rays and radio waves, but also in the visible light our eyes can see. This is the source of the beautiful light from these older remnants, the glow of a cosmic shock front. These shock fronts are also thought to be the galaxy's primary particle accelerators. They are the engines that create cosmic rays, which are not rays of light, but particles, protons and atomic nuclei that have been accelerated to nearly the speed of light. The mechanism is a bit like a particle surfing on the shock wave, being repeatedly bounced back and forth across the shock front by magnetic fields. With each bounce, the particle gains more and more energy, until it is eventually flung out into the galaxy as a high-speed cosmic ray. These tiny energetic messengers constantly rain down on Earth, a subtle, invisible reminder of ancient, distant explosions. But perhaps the most profound role of a supernova remnant is that of cosmic gardener. As we saw, the planetary nebula of a small star gently returns elements like carbon and oxygen to the cosmos. A supernova remnant does the same, but with a far richer and more violent generosity. It seeds the surrounding space not only with the basic building blocks of life, but also with all the heavy and precious elements forged in the star's final moments. This cloud of debris, rich with iron, silicon, gold and silver, will eventually slow down, cool and mix with the galaxy's existing gas clouds. This enriched material becomes the raw ingredient for the next generation of stars and planets. But the supernova doesn't just provide the ingredients, it can also trigger the cooking process. The powerful shockwave as it expands through space can compress nearby quiescent clouds of gas, pushing them past the tipping point where their own gravity takes over and they begin to collapse. The thunderclap from a star's death can become the catalyst for the birth of hundreds of new stars, and this brings this immense cosmic story directly home, to you, resting here, now. The fact that our planet Earth contains heavy elements like iron in its core, or that our own bodies rely on trace elements to function, is the most direct and personal evidence we have that our corner of the universe was seeded by an ancient supernova. The cloud of gas and dust that eventually formed our Sun, our Earth, and everything on it was not a pristine first-generation cloud. It was a recycled one, enriched by the death of at least one, and likely several, massive stars long ago. That long-dead star lived its brilliant fast life and died in a spectacular explosion, forging the very atoms that would one day come together to form the ground beneath our feet. The air we breathe, and the complex chemistry of life itself. We are not just stardust, we are, more specifically, supernova dust. A direct legacy of one of the most powerful events in the universe. As this beautiful, ghostly remnant expands outwards, carrying its precious cargo of new elements to seed the galaxy, we must ask ourselves a question. What became of the core? That impossibly dense ball of neutrons that bounced and created the shockwave, what was its fate? Did it also get blown apart? No. In most cases, it survived. The heart of the star, the stellar relic, remains. After the chaos of the explosion has passed, what is left behind is one of the most extreme and exotic objects in the entire universe. A neutron star. We have already met the substance of this object. It is that sphere of pure neutrons, forged in the crucible of the core collapse, held up against its own immense gravity by the quantum mechanical rule of neutron degeneracy pressure. It is, in essence, a single, gigantic atomic nucleus, 20 kilometers across, but containing more mass than our Sun. The properties of a neutron star are so extreme they stretch the limits of our imagination. We spoke of the density of a white dwarf, but a neutron star is orders of magnitude denser still. A single sugar cube-sized piece of neutron star material would weigh about 100 million tons. As much as a fleet of great ocean liners, compressed into a space you could hold in your hand. Its gravity is just as mind-boggling. The pull at the surface of a neutron star is hundreds of billions of times stronger than the gravity we feel here on Earth. The escape velocity, the speed needed to leave its surface, is more than half the speed of light. It is a gravitational prison from which escape is almost impossible. And then there is its spin. The original massive star, like our own Sun, would have been rotating, perhaps very slowly, completing one turn every few weeks or months. But as the core collapsed from a size larger than the Earth down to the size of a city, it brought that rotation with it. This is a principle called the conservation of angular momentum, and we can see it in a simple, elegant way on Earth. Think of an ice skater spinning. When her arms are outstretched, she spins slowly. When she pulls her arms in close to her body, her spin speeds up dramatically. The collapsing core of the star is the ultimate example of this. It can end up spinning at incredible speeds, rotating not just once a second, but hundreds of times every second. This collapse also concentrates the star's original magnetic field, crushing it down into that tiny volume. This creates a magnetic field of breathtaking power, trillions of times stronger than the Earth's. This field is so strong it would warp atoms and distort the fabric of space-time around it. So we have this tiny, super dense, super magnetic, rapidly spinning ball left at the centre of the explosion. But how would we ever see such a small object from light years away? We see it because of a phenomenon that turns it into a cosmic lighthouse. The neutron star's intense magnetic field can funnel particles into powerful beams of radiation, mostly radio waves, that shoot out from its magnetic poles. Now, if the star's magnetic poles are not aligned with its spin axis, which is usually the case, these beams will sweep around the sky as the star rotates. If we on Earth happen to be in the path of one of these sweeping beams, our radio telescopes will detect a pulse of energy every time the beam points towards us. One pulse with every single rotation of the star. From our perspective, it looks like a star that is flashing with perfect metronomic regularity. This is a pulsar. It is not a star that is actually pulsing. It is a steadily shining beacon that appears to pulse because of its rapid rotation. This very discovery was made in 1967 by a graduate student named Jocelyn Bell Burnell. While analysing data from a new radio telescope, she found a signal that was pulsing with such astonishing regularity that it was hard to believe it was natural. For a short time, the signal was half-jokingly nicknamed LGM1, for Little Green Men, as it seemed like it could be an alien beacon. But soon, more were found, and scientists realised they were seeing the signature of these incredible spinning neutron stars. And to bring our story full circle, let's return to the Crab Nebula, the remnant of the supernova seen in 1054. At its very heart, astronomers have found a pulsar, a rapidly spinning neutron star flashing 30 times every second. That is the leftover core of the star that exploded 1,000 years ago. The energy pouring out from this pulsar is what illuminates the inner regions of the nebula, keeping its ghostly form shining brightly even after all this time. It is the engine at the heart of the echo. Of course, let us return to the heart of the supernova, where the tiny spinning neutron star holds itself against the pull of gravity. Chapter 9, Beyond the Brink, the Birth of a Black Hole. The neutron star is a monument to balance, a tiny city-sized object held in perfect equilibrium by the immense power of neutron degeneracy pressure, a quantum mechanical bulwark against the final total victory of gravity. And for many massive stars, this is where their story ends, as a quiet spinning pulsar at the heart of an expanding nebula. But this raises another deeper question. Is a neutron star the final state for every massive star? What happens if the original star is so massive, so titanically large? The collapsing core it leaves behind is simply too heavy. What happens if even the incredible stubborn power of neutron degeneracy pressure isn't enough to halt the collapse? There is indeed a limit. Just as a white dwarf has a maximum possible mass, so too does a neutron stoichioid star. This threshold, known as the Tolman-Oppenheimer-Volkoff TOV limit, is thought to be somewhere between 2 and 3 times the mass of our Sun. If the leftover core from the supernova explosion is heavier than this, then there is no known force in the entire universe that can stop what happens next. The collapse continues. Neutron degeneracy pressure fails, and gravity at last becomes absolute and unopposed. The core continues to crush itself smaller and smaller and smaller still. To understand what this means, we need to gently reshape our understanding of gravity itself. The great insight of Albert Einstein was that gravity isn't a force in the traditional sense, but a curvature, a warping of the very fabric of reality. Imagine that space-time, the 3 dimensions of space and the 1 dimension of time woven together, is a flat, stretched rubber sheet. A massive object like a star placed on this sheet creates a dip, a gentle depression. A planet orbiting that star isn't being pulled by an invisible rope. It's simply following the curve in space-time created by the star, like a marble rolling around the edge of the dip. Now, think back to our collapsing stellar core. As it shrinks, the dip it creates in the rubber sheet of space-time becomes deeper and steeper. A white dwarf is a deep well. A neutron star is a profoundly deep and narrow well. But when the core collapses beyond the neutron star limit, the well just keeps getting deeper. The curvature of space-time becomes more and more extreme until it plunges downwards infinitely. The object crushes itself down to a point of zero volume and infinite density. This is a singularity. It is not a place you can point to, but a moment in space-time where all the mass of the core is concentrated into a region so small it has no dimensions at all. At the singularity, our known laws of physics, of space and time simply break down. It is the ultimate mystery, a point where our science falls silent. As this singularity forms, its infinite gravity warps the space-time around it so severely that it twists it shut. It creates a perfect one-way membrane, a boundary from which nothing can escape. This boundary is the event horizon. It is the true point of no return. On our rubber sheet analogy, it is the point where the slope of the well has become perfectly vertical. Anything that crosses this boundary, be it a spaceship or a beam of light, is trapped forever, destined to fall towards the central singularity. This entire structure, the singularity at the centre, and the event horizon that cloaks it, is what we call a black hole. It is black because light itself, the fastest thing in the universe, cannot escape its gravity once it crosses the event horizon. It is important, though, to picture this gently. A black hole is not a cosmic vacuum cleaner, aggressively sucking in everything in the galaxy. Its immense gravity is only truly inescapable very close to it. If our sun were to magically be replaced by a black hole of the exact same mass, the Earth and all the other planets would continue to orbit it just as they do now. We wouldn't be suddenly sucked in because we are far outside its event horizon. We would just find ourselves in a very cold, very dark solar system. The size of this event horizon is called the Schwarzschild radius, and it depends on the mass of the object. To turn the Earth into a black hole, you would have to crush its entire mass down to the size of a marble. To turn our sun into a black hole, you would have to crush it into a sphere just 3 kilometers, less than 2 miles across. This is the level of extreme compression that is required, a compression that only the death of the most massive stars can achieve. So we have this object, this sealant dark sphere in space, defined only by the boundary from which nothing can return. It is a scar left on the universe by the death of a truly massive star. But what would it be like to take a quiet, imaginary journey towards one? What would we see and feel as we approach this ultimate edge? Let's imagine we are in a small, peaceful vessel, drifting slowly closer. From a great distance, the black hole is invisible, a patch of perfect blackness against the starry background. Its presence is only given away by its gravity, which subtly alters the cosmos around it. The light from distant stars and galaxies that passes near the black hole is bent by its powerful gravitational field, much like a glass lens bends light. This effect is called gravitational lensing. The view of the universe behind the black hole becomes distorted, creating strange and beautiful celestial mirages. A single star might appear as a ring of light, or in several different places at once. It is as if we are looking through a cosmic funhouse mirror, a window warped by the gravity itself. As we drift closer, a stranger and more profound effect begins to take hold. According to Einstein's theory of relativity, time itself is affected by gravity. The stronger the gravity, the slower time flows. This is gravitational time dilation. For us in our little ship, Our watches would seem to tick along perfectly normally. We would feel no different. But for a friend watching us from a safe distance, far away from the black hole's influence, something remarkable would be happening. They would see our clock begin to tick more slowly than their own. As a consequence of this, the light from our ship would also appear different to our distant friend. As the light travels away from us, it has to climb out of the black hole's powerful gravity well, and in doing so it loses energy. This loss of energy causes the light's frequency to decrease, shifting its colour towards the red end of the spectrum. Our friend would see our ship become redder and dimmer. Now, let's imagine our journey's end is the event horizon itself. As we get closer and closer to that invisible line, our distant friend would see our clock slowing to a near-perfect stop. They would see our image become infinitely red-shifted, fading from view. From their perspective, we would appear to slow down, hover, and freeze for all eternity at the edge of the black hole, a faint, static image that never quite crosses over. We would become a part of the black hole's surface, frozen in time. But for us, in our ship, the experience would be very different. There is no frozen moment. We would continue our fall, reaching the event horizon at a perfectly normal time on our own watch. But as we approach, we would feel another more physical effect. The immense gravity of the black hole would be pulling on the front of our ship much more strongly than on the back. These powerful tidal forces would begin to stretch our vessel. This process, known by the wonderfully descriptive name spaghettification, would gently but irresistibly stretch any object that falls into the black hole into a long, thin stream of atoms. It's not a violent tearing so much as a fundamental unravelling by the steep gradient of space-time itself. It's a gentle thought to know, however, that for the very largest supermassive black holes that live at the centres of galaxies, these tidal forces at the event horizon are actually quite weak. One could, in theory, cross the event horizon without being spaghettified at all, only feeling those forces as you get much closer to the central singularity. For us, crossing the event horizon would be a quiet and unremarkable moment. There is no wall, no signpost. It is simply an invisible line in space, but once we cross it, the laws of physics and the nature of reality are fundamentally changed. Outside the black hole you can travel in any direction in space you wish. But once you cross the event horizon, all paths, all possible futures, lead in only one direction, towards the central singularity. It is as inevitable as the flow of time itself. In a way, inside a black hole, space and time have swapped their roles. The path to the singularity is no longer a direction in space, but a moment in your future. The story we have told so far paints a picture of a black hole as a place of absolute finality, an eternal prison for matter and light, a one-way journey to a central singularity from which nothing ever returns. For a long time this was the accepted scientific view. A black hole was a perfect eternal object defined only by its mass, its spin, and its charge. But this elegant, simple picture was missing a piece of the puzzle. It didn't account for the strange and wonderful rules of the quantum world, and when the brilliant mind of Stephen Hawking brought the two together, the picture changed forever. He showed us that a black hole is not in fact perfectly black, and it is not in fact eternal. To understand this, we must zoom in on the fabric of space itself, right at the edge of the event horizon. In the world of quantum mechanics, empty space is not truly empty. It is a bubbling, fizzing sea of energy, where tiny pairs of particles and their antimatter counterparts are constantly popping into existence. These are called virtual particles. They exist for an impossibly short moment, borrow a tiny bit of energy from the vacuum, and then almost instantly collide with each other, annihilate, and pay the energy back. You can think of it like tiny shimmering bubbles that form and pop in a fraction of a second in a pot of water. All of space is filled with this gentle, constant hum of quantum activity. Now, imagine one of these virtual particle pairs pops into existence right at the very edge of a black hole's event horizon. Usually they would annihilate each other immediately. But here, something else can happen. It's possible for one particle of the pair to be captured, falling across the event horizon into the black hole, while the other one escapes, flying off into space. To a distant observer, it would look as though the black hole had just emitted a particle. But this creates an energy problem. That escaped particle is now a real particle, flying through space with real positive energy. That energy has to come from somewhere. The universe must balance its books, and it does so in a beautiful way. The particle that fell into the black hole is considered to have negative energy, and when it is absorbed, it subtracts a tiny, tiny amount of mass from the black hole itself. In essence, for the escaping particle to become real, the black hole must pay the energy price, and it pays for it with its own mass, according to Einstein's famous equation E = mc2. This steady, incredibly faint stream of particles being radiated away from the event horizon is known as Hawking radiation. It means that a black hole is not perfectly cold, it has a temperature, and it glows with a faint thermal energy. For a black hole with the mass of a star, this temperature is incredibly low, far, far colder than the background temperature of space itself, so it's actually absorbing more energy than it radiates. But it is radiating nonetheless. And this leads to the most profound conclusion of all. If a black hole is constantly losing energy and mass through Hawking radiation, then it must be slowly, incredibly slowly evaporating. The timescale for this process is almost beyond human comprehension. For a typical stellar mass black hole, the time it would take to evaporate completely is around 1067 years. That's a 1 followed by 67 zeros. It is a number so vast that the current age of the universe, 13.8 billion years, is an insignificant speck by comparison. But if we could wait, we would witness a final remarkable act. As the black hole loses mass, its temperature increases and the rate of evaporation gets faster and faster. In the final fraction of a second of its existence, when it has shrunk to a microscopic size, it would release all of its remaining mass energy in a final brilliant flash of high-energy gamma rays, a quiet burst of light, returning everything that ever fell into it back to the universe. This idea, however, leaves us with one last deep and gentle puzzle that scientists are still pondering today. It's called the black hole information paradox. If a black hole evaporates and only this random thermal Hawking radiation comes out, what happened to the information about what fell in? The universe, we believe, doesn't lose information. So how can the very specific information of a star or a spaceship be converted into random heat? We don't yet know the answer. It is a quiet mystery, a whisper that tells us there is still so much more to learn about these incredible dark children of dying stars. Our journey tonight has been a long one, across billions of years and unfathomable distances. We have seen how stars live in a delicate balance, and how their deaths, whether gentle or spectacular, are not moments of destruction but acts of creation. Every planetary nebula, every supernova remnant, is a promise. It is the universe renewing itself, taking the ashes of one generation and using them to build the next. The story of the stars is the story of us. The same cycle of creation, existence, transformation, and legacy is written into everything. The universe is not something distant and separate from you. You are woven from its very fabric. The quiet, steady rhythm of your own heart is a distant echo of the steady fusion in a star's core. The gentle rise and fall of your breath is a part of the same cosmic dance. So for now, let these vast and cosmic thoughts gently dissolve. Let them become a soft, comfortable blanket of wonder. There is no need to hold on to them, no need to remember the details. Simply allow the feeling of connection to remain. A sense that you're a part of something ancient, beautiful and unending. Just as the day finds its rest in the quiet of the night, allow your mind to find its rest now, knowing that even in stillness you are a part of this incredible dynamic cosmos. If our time together tonight brought you a sense of calm or wonder, I would be so very grateful if you considered leaving a gentle like. And perhaps, if you wish to join me on more quiet explorations, you might even subscribe to our channel. It helps our small community of sleepy wanderers to grow, but all of that can wait. The most important thing now is your peace and your rest. Let the vast, quiet, stardusted darkness hold you. Let go of the day and drift peacefully on the gentle currents of sleep. Sleep well, dream of stardust, and until next time, keep wondering.